Now I'm going to introduce another data structure called a binary tree. Trees in general just represent some type of hierarchical relationship. So at the top you have what we would typically call the root, if we're talking about it in the computer science sense. But each of these circles here is a node, and the root here is a parent node that has these two children. Manager 1 also has its own children, Manager 2 has its own children, and this could continue on. Of course, you recognize organizational charts like this, which is technically a tree. There's other uses for trees out in the non-computer science world. We use them for diagramming grammar. That is, you take a sentence and you show the relationship between the words in the sentence. But even in computer science, you can take the things that you've written in a programming language and represent it as a tree. And in fact, people actually do that. And then even mathematical expressions can be represented using a tree. And this also happens in the programming sense at times. So how do we understand this expression right here? Well, it can be represented like this, where we say, okay, 2 and 3 are connected by the binary operator plus. The result of this, which is 5, then is related to 4 via the subtraction operator here. We could take the same thing and say, well, this is equivalent to 3 minus 4, and then that gives us minus 1, and then 2 plus minus 1 will be 1. So both of these give me the same result, but it's two different ways to represent this expression. In terms of how many child nodes a tree can show for each parent, that can vary, but I'll only talk about what are called binary trees. So in binary trees, each parent has at most 2 children. So you can see this right here has 2 children, this has 2 children, this has 2 children, 5 has 0 children, 6 has 0, 7 has 0. These could be sort of lopsided, so each of these could have 1 child. That would be fine. And then when we get to what's considered the bottom level, these are called leaves. So there's a leaf, a leaf, a leaf, a leaf, a leaf. All right? So how do we create a binary tree? If you've seen my video on constructing linked list, you saw that we did it by allocating memory for nodes and then chaining those nodes together by storing the address of one node inside another node. Well, in that case, each thing was connected to exactly one other node, at least for the singly linked list. For binary trees, we need to potentially store 2 addresses. So a structure definition for a node might look like this in the simplest case. Something that stores our data, which is the whole point of having the tree in the first place, and then being able to store the address of the left node and the address of the right node. So let's see this in action. So we'll say D here will be for my data, struct node, star left, struct node, star right. So there's my structure definition. And we'll say struct node, star root. Technically I don't need, for the way I'm going to construct it, I don't need to set it to null, but we could. And now I'm going to hand construct the tree. So let's say we have something that looks like this. Let's draw a picture first. So let's say we have 5. Over here maybe we have 10. And this is 23. And that's 4, 8. These would be stubs for nulls. And then we'll say this is 15, 30. And we'll leave it at that. All right? So that's the tree I want to construct. Now we don't know yet an automated way of doing it, so that's why I'm going to hand construct it. Get out of this. All right, so how do we create the root node, which is the top node? So root equals, and then we'll have a function here called add node that needs the value to store. So we said it was 5. So let's create that function. So its return type has to be this, struct node star. and it gets an int, which I'll call n. So what needs to happen? If we think about what I have here, I need to allocate memory for the entire structure. Then I need to store our value or our data and then do something with left and right. And so initially, they'll be null. So struct node star temp equals malloc. Size of a struct node. And now we can say temp D is equal to the number passed in, and temp left is equal to null. Same thing for right. And eventually we'll do this. Return temp. So that way we'll say root equals this node. So why the nulls? We're coming back to this. When we create the first node, then I'm basically doing this. 5. Because we don't know yet if I'm going to have child nodes. So I want to go ahead and set these to null, which is what these represent. And then if I want to add like 10, well then I just create the 10, set it to null, and then we tie this together, breaking the null. So I'll just say the left component of this is equal to the address of this. That's how I tie it together. So here's my function. And so how do I do what I just described? Well, without some type of automated process, which is what you really want, I'm going to do this. I know there's a left component to this, so I'm simply going to call add node again, giving it that 10. And when temp returns the address, I assign it to root left, just like I showed you in my picture. And then we'll do the same thing for right. And for what I gave you, that was 23. And what about each of these? I can do the same thing. So I can chain these together and say this was 4. Add node 8. And then for this would be left. Be 1 for right. I need to add the values. This will be 15 and 30. All right? So that's just constructing a tree. How do we see what the values are in the tree? Well, that's what we need to talk about next, is how do you traverse the tree? So there's a variety of ways to do it, but probably the two most common ways would be what are called breadth first traversal and depth first traversal. So basically what breadth first traversal does is you move down one level at a time, processing every node at that distance from where you started. Depth first traversal moves down a chain, and then when it can't go any deeper, at least in the simplest version, then it backtracks to where it split and it follows something else. So let's see conceptually what breadth first search is. So if I have this right here, this tree, then breadth first traversal says, okay, we'll start with 5, because that's 0 nodes away from where we start, because this is really the root. So we process everything at this level, which is just 5. And now then we want to process everything that's 1 node away from this, so that's this level. Then everything at this level, and so forth. So if I had something like this, and then this had nodes, then the next level would be this, and then finally this. That's breadth first search. All right. In depth first search, we start someplace like 5, and then I start working my way down. So I start at 5, and if I'm doing it left to right, I go down, I got to 10, I go down to 4, I come down here, hit null, backtrack, look over to here, backtrack, come back to 10, come down to 8, this way, backtrack, come here. Now I go down this side, do the same thing. So this is more like you might think of if you have a maze. So if I come in here and say there's, things like look like this for different paths. You might come all the way down. You eventually hit essentially a roadblock. You come up, you come over here, maybe you come over here, you backtrack, come over here, go this way. Eventually you backtrack, come back to here, that kind of thing. All right? So let's see these in action, or at least talk about, well, how do we do breadth first search and how we do depth first search. Conceptually, breadth first search is this. We're going to add root to a queue. If you don't know what a queue is, I have a video on that in which I construct a queue using a linked list. And so what we'll do is we'll add root to the queue, and then as long as the queue is not empty, we're going to remove the first thing from the queue, which is dequeuing. So we take that node, do something with it, but then we also, before we completely destroy it, add the left and right child of the node to the end of the queue. All right? So let's see that in action. So my tree, once again, that I had here, in fact, we'll change it slightly to give me some variety. So we had 10, 23, 4, 8, 15, 30. Let's say this had another node, 91. There's nothing here, so it's just null. And then maybe nothing there. And then maybe over here we have 100 and 50. So breadth first search says what should happen is you go at this level, this level, this level, and that level. So our algorithm was we create a queue, and as long as it's not empty, we add nodes. And so we start with the root, which is 5, and then when I use this, add its 2 child nodes. So we'll mark these off, 5, and then we put 10 and 23, and now we use 10, so I add its 2 children, 4 and 8. Use the 23, so I add its children, 15 and 30. Next one is 4. So see, I'm working down a level at a time from left to right. 4, it has no children. 8 has no children. 15, I use that, so I add 91. Right? 30, so I add this child, which is 100. Then 91, no children. 100, use it, add this child, 50, it has no children. And so we use it up, and now we've processed every node in the tree. So it was one level at a time. All right? So that's one way of doing it. Now let's look at the depth first search and see how that works. So it turns out there's 3 basic ways to implement depth first search. Because as I work down the nodes, what the real issue is at what point do I use the current node? So when I get to a node, say we do this right here, I'm at 5 to start with, this is my root. Do I use 5 now and then explore the child nodes? Or do I use 5 after I've explored either both child nodes or one of the child nodes? That's the difference between the 3 different versions. So our traversals are pre-order, in order, and then post-order. And let's see this in action. So here once again is the definition for the function, and this is going to use recursion. In my recursion video, I showed you a number of examples, and I said that some of the classic examples really, in my opinion, aren't very good at making you a believer in the usefulness of recursion because they're easy to avoid. this will be very, very difficult to avoid using recursion, because we're going to rely upon the runtime stack to keep track of where we're at. Because when I say follow the left child, I'm going to call this function again. And so when I get back, I need to pick up where I left off, which is now to follow the right child. Right? So as we see each of these three traversal methods, notice that the only way they are different from each other is where the use current node is at. So in pre-order, we use their current node as soon as we get to the node, before we've explored the left and right child. In order says that we then go left first, and then as we come back to the current node, that's the one that called left, we use the node for whatever we have to do with it, and then we go right. And then finally, post order says we deal with the left and right children first, then use the current node. Now note that in all of these, I've said go left, go right. If you had a certain application, you certainly could go right before left. Just like here, when I add the left and right children, I could have added the right and left child if that's what I want to do. This is just a convention, is to go left and right. Right? So let's see these in action. So let's talk about conceptually and then write code to do it, because I want to print this true. Or let's actually implement these and then explain how it works. So printf pre-order I need root here. So this one will be in order. This will be post order. All right. So let's start writing functions. So there's no return value, but they expect to receive a struct node star. So void pre-order struct node star, and I'll call this root here, even though it's technically a different root variable. So what do we say? If not null, then do this stuff. So I'm going to turn that actually into, I could write that, but I'm going to turn it in this instead. If root equals null, return. Right? And then, if we're not returning, then do what's here, which means it's not equal null. So conceptually, it's basically the same thing. So pre-order says use the node first, and what I'm going to do is simply print the value. So we'll do printf. And what was my structure definition? So D is my variable. Let me format this a little more. So %D. And what I'm printing is root D. And then I'm going to call pre-order again, use recursion. So this is my stopping mechanism for the recursive calls, because you need that, otherwise things blow up. So pre-order, I'm going to go left first, and then I'll go right. So these don't happen concurrently. When we get here, this is on the stack, so I'm going to print, and then I'm going to call this function again, which pushes another instance of it onto the stack, where I'm going to have the left address stored in what's called root. And then when I finish working my way completely down a certain chain and return to this point, then I'll go right. Right? So there's the pre-order. Let's look at the other two. So we'll make this in order, which means this needs to be changed. And the order needs to change. So in order, use the node in order. And now post order says use the node after you're done doing or processing the child nodes. So it'll be post order. use it when I get back. So I have everything here, I think, that I need. So now let's see what this does. So there's the values. Let me write this down. So for our tree, I'm going to copy this down and then write these values, and then we'll see if it matches up. So I guess you can get something to drink or whatever while I do this. So this will be, we said 5 was at the top. Then we had 10 that had 4 connected to it. 10 also went to 8. Then the right child of 5 is 23. Its left child is 15. And its right child was 30. And then here we've said, or actually let's just work it out on paper and then we'll come back and compare it since you would have just seen it. All right. So pre-order. Pre-order says, as soon as I reach the node, I use it, then I go left, and then when I get back, I'll go right. So I start here. This is my route. So I start here, so I have 5. And then I go left. I'm at the node the first time, so I want to use it. So 10. I go left. I'm at the node for the first time, so I use it. 4. Then I go left. This is where I hit the instance of the function where I say if null, return. So now I return to 4, and I follow its right child. Well, that's also null, so I return. So now I'm at the bottom of the function call, so I want to return to where I came from, which is 10. So now I follow the right child of 10, which is 8. I follow the left child of 8, which is null. Follow the right child of 8, which is null. Come back to 10. Now I followed both the left and right children of 10. So I return to where I came from for this, which was 5. Now I follow its right child, which is 23. Then I follow its left child, which is 15. Follow its left child, which is null, return. Right child, null, return, return. Follow its right child for 23, go to 30, use it. Follow its left child, return. Follow its right child, return. And then I return, then I return, then I'm back at main. So is that match? 5, 10, 4, 8, 23, 15, and 30. Just like I've got on my piece of paper here. All right? So now what about in order? So let's draw a picture of what's going to ultimately happen. So I have 5, and I have 10, and I'm going to go down this way. And eventually I have to come over here and have 23. What happens here is that I get to 5, but I don't use it yet. So I follow left, and I'm going to deal with everything on the right-hand side. And so as I pass through 5 to get to the 23, that's when I use 5. So I've already dealt with the left-hand side completely. Then I'm back to the part of the function that's on the stack for 5. That's when I'm going to use the node, which in our case is printing. Then I pass through and go over here to 23. So that's what in order does. So for in order, 5, go left. 10, go left. 4, go left, hit null. Then when I return 2, as I'm passing through, I'm going to use the node, so I have 4. Deal with the right node of 4. Return. So now I return back to where I came from, which is 10. So as I pass through, I'm going to use the 10. Get to 8. Go left. Hit null. Return. As I pass through, I use the 8. And then go right. Return. Return. Now as I pass through 5, I'm finally going to use it. Come to 23, go left. Come 15, go left. Hit null. Return. So I'll pass through 15 and use it. Sorry, this should be 15. Go right, hit null, return. Return to where I came from, which is 23. As I pass through, I'm going to use the 23. Go to 30, go left, hit null, return. As I pass through, I use the 30. Go right, hit null, return, 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 and I have this right here. So come back and look at what my program printed. We can see it's 4, 10, 8, 5, 15, 23, 30. Just like on my piece of paper. And then finally, post order. So post order says go left, go right, then use the current node. So we start at 5, go left. Hit 10, go left. Hit 4, go left. Return. Now we go right. Return. So I've already hit the two children of 4, which both had values of null. So now that I'm back to 4, I use the 4. So then I return to 10. Now I go right to 8. Deal with the left child of 8, hit null, return. Deal with the right child of 8, return. Now I use the 8. Now I return to where it came from, which is 10. So I've already dealt with the 4 and the 8 that are the children of 10. Now I'm ready to deal with 10. Return to where he came from, which is 5. Go right to 23. Go left to 15. Go left to null, return. Go right to null, return. Use 15. Return to where you came from. Go right of 23, which is 30. Go left of 30, hit null, return. Go right of 30, hit null, return. Now I'm ready to use the 30. Return to where you came from, which is 23. So I've dealt with 15 and 30. So I'm ready to use 23. Return to where it came from. Well, I've dealt with 10 and 23. So I'm ready to use 5. Looking at what my output was. 4, 8, 10, 15, 30, 23, and 5. That's how that works. So one thing I didn't do here is free up the memory for my tree. So how would I do that? Well, let's think about what I just did. At what point can I free things up? If I do this and say free root, which is perfectly legal, what happens? Well, I just lost track of the left and right children of the tree or of that root node, and now I don't know where they're at, so I can't free up the memory. Because remember, each of these 7 calls to add node allocated memory, so technically I need 7 calls to free. So what process should I use? Well, we want to process the tree in reverse order. So we come back to my tree. I want to free up this, 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 and this before I hit the next level. Now the order in which I do these doesn't matter. I could do 4, 30, 15, 8. It would still work. I just don't have an easy way of doing that. But in terms of getting things to free up all memory, that would be fine. But I want a systematic process. So I want to free up 4 and 8 before I free up 10, 15 and 30 before I free up 23. So once I freed up 4 and 8, then I can free up 10. Once I've freed up 15 and 30, then I can free up 23. Now that I've freed 10 and 23, I can free up 5. Well, what did I just do that visited the nodes in that way? Post order. 4 and 8, then free 10. 15 and 30, then free 23. 10 and 23, then free up 5. So I'm going to take my post order traversal function and modify it to free the nodes. That's one of the applications there of that particular traversal method. So let's come down here and say free mem, in which I'll give it the root to start with. And now I'm going to copy this function. Free mem, I need to make sure I change these function calls. I'm freeing the node with this value, and finally free root. So let's see if that still compiles and runs. Really need a new line in here, so let's put that in here to make it easier to read. And we'll do this. And there we go. So I freed them in that order, and there's the traversal methods. So that's the way of traversing using depth first search. So I just showed you the 3 standard ways. There are modifications to some of those, but I'm not going to get into that. All right. Let's talk about one last thing. Binary trees have a number of uses, but one of those uses is to search the binary tree in an efficient way. The problem with what I've shown you here is that we can't easily search. So let's revisit what I wrote here. And so imagine I want to search for, say, 15. So I might start the root, but then what do I do next? Well, the order in which I added these nodes with these values is somewhat random, right? So for all intents and purposes, I basically have to look at everything. So either I find it along the way, so maybe I use my traversal I just showed you. So I look at 5, nope, that's not. 15, look at 10, that's not. Look at 4, that's not. Maybe come back, look at 8, no, that's not. Come back over here, look at 23, nope. 15, well, just found it. So in this particular case, I searched all but one node. If I've been searching, say, for 99, the only way to know that's not there given this tree is to look at every single node and then conclude that I couldn't find 99, so it's not there. Is there a way to make this easier? Well, there is. So there's two useful properties that we would like binary trees to have if we intend to search them. What I showed you could be fine for certain applications, but search is one of the primary uses of binary search trees, or that is for binary trees. If we have what's called the binary search tree property, then it's called a binary search tree. But even then, that can be messed up if we also have a balanced tree. So I'll discuss these more in another video because this is getting kind of long. But we won't go into a lot of details about balance because trying to balance a tree is really beyond the scope of what I'm trying to teach. That's really something you need to see in a data structures course. But the binary search property is fairly easy to implement, and so we'll look at that in another video.